Turning our attention to Chapter 10, Dynamic Scaling, Orchestration with Kubernetes Autoscalers. Let's discuss theoretical foundations. The theoretical foundation for orchestrating and scaling containerized AI agents rests upon the principles of declarative state management, event-driven elasticity, and resilient service communication. In a cloud-native ecosystem, an AI agent is not merely a static executable, it is a dynamic entity whose lifecycle, creation, scaling, healing, and termination, must be automated to handle the stochastic nature of inference workloads. Unlike traditional web servers where traffic is relatively predictable, AI inference often suffers from burstiness, where a sudden influx of requests, e.g., a viral user-generated content event, can overwhelm static infrastructure, leading to high latency or dropped requests. To understand this deeply, we must first establish the architectural shift from monolithic AI deployments to distributed agent microservices. Now, let's explore the agent as a stateful microservice. In previous chapters, we discussed the decomposition of monolithic AI pipelines into discrete functional units, pre-processing, model inference, and post-processing. In Chapter 10, we elevate this concept by treating the inference unit itself as an autonomous agent. This agent is containerized, meaning it packages the model weights, the inference runtime, like ONNX runtime or PyTorch, and the C# orchestration logic into an immutable artifact. The why here is critical: isolation and density. By containerizing agents, we can pack multiple heterogeneous models, e.g., a text embedding model and a text generation model, onto the same GPU node without dependency conflicts. However, this density introduces complexity. How do we ensure that a spike in embedding requests doesn't starve the generation model of VRAM? This is where Kubernetes, the standard orchestrator, and C#, our language of choice for control logic, intersect. While Kubernetes provides the primitives, pods, deployments, services, C# provides the intelligence to manipulate these primitives dynamically. Now, let's explore the analogy, the smart highway system. Imagine a highway system where cars represent inference requests. Static scaling is like building a fixed number of lanes. If traffic is low, lanes are wasted. If a traffic jam occurs, the lanes are insufficient, and cars pile up indefinitely. Dynamic orchestration is a smart highway. The road surface itself is modular, containers. Sensors, metrics, monitor traffic density, queue depth. When congestion hits a threshold, the road automatically widens by snapping in new modular segments, pods. When traffic clears, segments detach to save space. Furthermore, there are dedicated lanes, GPU time, slicing, for sports cars, large language models, and buses, batch processing, ensuring they don't collide. Moving on to 1. Declarative state and the desired state loop. The core theoretical concept of orchestration is the desired state loop. In C#, we often think imperatively, if X happens, do Y. In orchestration, we think declaratively, I want the system to look like this. Using C#'s records, introduced in C#9 and refined in later versions, we can model the desired state of an AI agent cluster with immutable precision. This is crucial because the state of a distributed system is constantly converging toward, or drifting away from, this desired state. Consider the definition of an agent deployment. Here, we're defining a record called agent deployment. Notice the use of record in C#. This isn't just a class, it's a special type designed for immutable data. In cloud-native systems, immutability is a powerful concept. It means once an agent deployment object is created, its properties cannot be changed. This simplifies reasoning about state, especially in distributed environments where multiple services might be interacting with deployment configurations. For an AI agent deployment, having an immutable desired state ensures consistency and predictability. We define essential attributes like name, model artifact URI, where the AI model lives, and min replicas / max replicas for scaling. This structure directly supports the GitOps paradigm, where deployment configurations are stored in version control and treated as the single source of truth. Next, we define hardware constraint as another record. This nested record captures the specific hardware requirements for our AI agent. See how we specify required GPU cores and memory size. This is crucial for efficient resource allocation in a containerized environment. When deploying AI models, GPUs are often the bottleneck, and memory is also a significant factor. By explicitly defining these constraints, we enable the orchestration system, like Kubernetes, to make intelligent scheduling decisions, placing agents on nodes that meet their hardware demands. Without this, agents might be scheduled on under-resourced nodes, leading to poor performance or failures, or on over-resourced nodes, leading to wasted resources. This directly impacts the cost-effectiveness and performance of our AI inference services. Here, we define the scaling policy record, which is vital for the elasticity of our AI agents. It specifies scaling metric and target value. This policy dictates how our AI agent deployments will automatically scale up or down based on operational metrics. In a cloud-native architecture, horizontal scaling is a cornerstone for handling variable loads. An immutable scaling policy, defined as a record, ensures that the scaling behavior is consistent and auditable. Imagine if this policy could be changed dynamically without a clear record, it would be much harder to debug unexpected scaling behaviors or resource consumption spikes. This design promotes a declarative approach to infrastructure management. Finally, we have the scaling metric enum. This enumerates the different metrics we can use to drive our scaling policies. Notice the options: queue depth, inference latency (ms), and GPU utilization. These are very common and effective metrics for AI workloads. Queue depth indicates how many requests are waiting, inference latency (ms) directly measures performance from the user's perspective, and GPU utilization is a key indicator of GPU resource pressure. By providing these specific metrics, we enable fine-grained control over autoscaling, allowing us to optimize for cost, performance, or a balance of both. This design allows for different AI models or agent types to have different scaling strategies tailored to their specific operational characteristics, which is a hallmark of a flexible microservices architecture. Why this matters: in a previous chapter, Book 6, perhaps on microservice design patterns, we discussed the repository pattern for data access. Here, we apply a similar pattern but for infrastructure. The orchestrator's job is to continuously compare the actual state, number of running pods, with the desired state, the record above, and reconcile the differences. C#'s pattern matching features, switch expressions, are ideal for writing these reconciliation loops efficiently. Now, let's talk about 2. Horizontal pod autoscaling, HPA, and custom metrics. Standard horizontal pod autoscalers, HPA, in Kubernetes typically rely on CPU and memory. For AI agents, these are lagging indicators. A GPU can be at 0% utilization while the inference queue is backing up, if the batch size is small or the model is memory-bound. Therefore, the theoretical foundation requires custom metrics. We need to expose a metric like inference_queue_depth from the C# application to the orchestrator. The mechanism: 1. The C# agent. The agent runs an ASP.NET Core background service that pushes metrics to a Prometheus endpoint. 2. The adapter, a metrics adapter, often running as a sidecar or a dedicated service, scrapes these endpoints. 3. The controller. The Kubernetes HPA controller queries the adapter and scales the deployment. In C#, we use interfaces to abstract the metric emission. This allows us to swap between different monitoring backends, Prometheus, OpenTelemetry, Azure Monitor, without changing the core inference logic. Here, we define the iMetric emitter interface. This is a crucial architectural decision for promoting loose coupling and testability in our microservice. By defining an interface, we abstract away the concrete implementation details of how metrics are recorded. This means our core business logic, such as the AI agent processing requests, doesn't need to know if we're using Prometheus, OpenTelemetry, or a simple console logger. It just needs to know it can record a metric. This adheres to the dependency inversion principle, a cornerstone of robust, maintainable systems, especially in a cloud-native environment where observability backends might change. Now, let's look at the Prometheus metric emitter class, which implements our iMetric emitter interface. Specifically, at line 12, we see metrics, gauge, AI_agent_queue_depth, depth. This line uses a Prometheus client library to expose a gauge metric. A gauge is a metric that represents a single numerical value that can arbitrarily go up and down, making it perfect for tracking things like the current depth of a processing queue. In a cloud-native context, Prometheus is a de facto standard for monitoring. By exposing this metric, we enable external monitoring systems, like Prometheus itself, often deployed via a Kubernetes operator, to scrape this data from our microservice. This is vital for understanding the operational health and performance of our AI agent, allowing us to detect bottlenecks, scale resources appropriately, and ensure service-level objectives, SLOs, are met. The why of custom metrics: if we rely solely on CPU, we might scale up too late. AI inference is often compute-bound in bursts. By scaling on queue depth, we proactively add capacity before the latency degrades. This is the difference between a user waiting 200 milliseconds versus 5 seconds. Now, let's talk about 3. Zero downtime deployments and state transfer. When updating a model, e.g., swapping a version 1.0 model for a version 2.0 model, we cannot simply kill the old pods and start new ones. Inference is stateful, requests in flight must be handled gracefully. We employ two primary strategies here, both heavily reliant on C#'s graceful shutdown mechanisms. 1. Rolling updates. Kubernetes gradually replaces old pods with new ones. 2. Blue/green deployment. We spin up a full parallel environment, green, with the new model. Once verified, we switch traffic, via a service mesh, instantly. C#'s role in graceful shutdown. When Kubernetes decides to terminate a pod, during a rollout or scale down, it sends a SIGTERM signal. The C# runtime catches this. We must ensure that the I-host, in ASP.NET Core, stops accepting new requests but finishes processing the current batch. We begin by setting up our ASP.NET Core web application. Notice at line 2, web application.createBuilder, args, is the entry point for configuring our web host. This builder pattern allows us to register services, configure middleware, and set up various application behaviors before the application actually starts. Crucially, from lines 5 to 8, we are configuring host options, specifically options.shutdownTimeout. This is a critical setting for cloud-native applications, especially microservices that might be processing long-running tasks like AI inference. We've set it to 30 seconds. This timeout dictates how long the application will wait for ongoing requests to complete gracefully before forcefully shutting down during a redeployment, scaling down event, or node maintenance. Without this, in-flight inference requests could be abruptly terminated, leading to lost work or inconsistent states for the client. This contributes directly to the reliability of our agent. At line 10, build constructs the web application instance, which is essentially our HTTP request pipeline. Then, from lines 13 to 18, we introduce a custom middleware using AppUse. This middleware is designed to track active requests. While the current implementation shows placeholders for incrementing and decrementing a counter, the intent is clear, to monitor how many requests are currently being processed. This is vital for graceful shutdown procedures. Imagine if our shutdown timeout, configured earlier, expires, but we still have many requests in progress. A robust implementation would use this counter to inform the shutdown process, perhaps by delaying the actual shutdown until the counter reaches 0, or at least logging pending requests. This pattern supports cloud-native principles of observability and graceful degradation. Look at line 20, app map post, /infer, async, inference request req, equals. Defines an HTTP post endpoint for /infer. This is where our AI agent will receive inference requests. The async keyword indicates that this operation will likely involve I/O-bound or CPU-bound tasks that can be asynchronous, preventing thread blocking. Inside the lambda, the comment // heavy computation at line 22 signifies that this is where the actual AI model inference would occur. This is typically a CPU-intensive operation, potentially taking significant time. Finally, at line 26, await app run async, starts the web application and blocks until the application is shut down. The await here is important. It ensures that the main thread doesn't exit prematurely, allowing the web server to process requests. The combination of the shutdown timeout and this run async call means the application will attempt a graceful exit, respecting the configured timeout for in-flight requests. Why this is critical for AI, GPU memory operations are not instantly interruptible. If a model is halfway through a forward pass, killing the process abruptly leaves the GPU in an undefined state or locks memory. The graceful shutdown window allows the C# runtime to dispose of the idisposable model resources correctly. Now, let's explore 4. Resource optimization, GPU sharing and time slicing. A theoretical challenge in AI orchestration is the granularity of resource allocation. A modern GPU, e.g., NVIDIA A100, is a massive resource. Assigning a full GPU to a small, lightweight agent, like a sentiment analysis model, is wasteful. We solve this using GPU partitioning or time slicing. While this is often configured at the driver level, the C# application must be aware of its constraints. We use environment variables injected by the orchestrator to inform the C# agent of its slice of the GPU. Here, we define a simple C# class called GPUConfig. This class serves as a configuration holder for GPU-related settings, specifically designed to interact with the environment variables typically set in a containerized, cloud-native environment. Notice how we're directly initializing properties using environment variables. This is a common pattern in 12-factor apps and cloud-native development, promoting configuration externalization rather than hard-coding values. It allows us to easily change GPU settings without rebuilding the application, which is crucial for flexible deployments and horizontal scaling in environments like Kubernetes. The analogy, this is like timesharing a vacation home. Instead of owning the whole house, GPU, you own a specific week, time slice, or a specific floor, memory partition. The C# code must respect these boundaries. It cannot allocate memory beyond its assigned slice, or the orchestrator, via the kernel, will kill the process. Turning our attention to 5. Service mesh and inter-agent communication. In a distributed inference pipeline, agents talk to each other. For example, a orchestrator agent might call a tokenizer agent, which calls a model agent. The theoretical foundation here is service discovery and resilience patterns, circuit breaking, retries. While Kubernetes services handle basic load balancing, a service mesh, like Istio or Linkerd, injects a sidecar proxy next to our C# agent. The C# agent communicates with the proxy via localhost. C# HTTP client and resilience, modern C# IHTTP client factory, combined with libraries like Poly allows us to implement resilience strategies directly in the agent code, complementing the service mesh. Here, we're setting up a retry policy using the Poly library. This is a critical component for building resilient cloud-native applications, especially when dealing with microservices. We're configuring it to handle transient HTTP errors, which are temporary network issues, and also specifically too many requests, HTTP 429, status codes. The wait and retry async part specifies an exponential backoff strategy. It will retry 3 times, waiting for 2, 4, and 8 seconds respectively between retries. This pattern prevents overwhelming a downstream service during temporary outages or rate limiting, which is essential for stable operations in distributed systems. This call downstream agent method demonstrates how our agent utilizes the retry policy we just defined. Notice at line 10, we wrap the actual HTTP call within retry policy.executeAsync. This means any call made to a downstream agent through this method will automatically benefit from the configured retry logic. This is a powerful abstraction, as the calling code doesn't need to worry about retries, it's handled declaratively. The comment at line 12 is also very insightful. In a cloud-native environment, particularly with a service mesh like Istio or Linkerd, this HTTP call would typically be intercepted by a sidecar proxy. This sidecar can add further resilience, observability, and security features transparently, complementing our application-level retry policy. This layered approach to resilience is a common and robust cloud-native pattern. Why this matters: in a distributed system, network partitions are inevitable. If the tokenizer agent is down, the model agent shouldn't hang indefinitely. By using C#'s modern async/await patterns combined with resilience libraries, we ensure the agent remains responsive and fails fast, allowing the orchestrator to potentially reschedule the workload or return a graceful degradation message. Now, let's explore theoretical foundations. The theoretical foundation of this chapter implies a shift in how we write C# code for AI. 1. Idempotency: code must be idempotent. If a request is processed twice due to a retry, the model output should remain consistent. 2. Observability: code must emit telemetry. We cannot debug a distributed system without structured logs and metrics. 3. Decoupling: logic must be decoupled from infrastructure. The C# code should not care if it runs on a single GPU or a cluster of TPUs, it should rely on abstractions, interfaces, and environment configuration. By mastering these patterns, we move from running scripts to engineering systems that can autonomously scale to meet the demands of global AI workloads. Moving on to basic code example. Let's consider a scenario where an AI agent performs sentiment analysis on user reviews. During a flash sale, the number of incoming reviews spikes dramatically. A single container cannot handle the load, leading to timeouts and dropped requests. We need a mechanism to automatically scale the number of agent instances based on the current workload, queue depth, rather than just CPU usage. Here is a self-contained C# example simulating a Kubernetes horizontal pod autoscaler, HPA, using a custom metric, inference queue depth. This code uses modern C# features like top-level statements, system, threading, channels, and IAsync enumerable. We begin by importing necessary .NET namespaces. System, collections, concurrent is crucial for thread-safe collections, which we'll see used later in our orchestrator for managing agents. System, threading, channels provides powerful, asynchronous, thread-safe primitives for producer-consumer patterns, which are ideal for handling request queues in our AI agents. Finally, public record sentiment request, GUID-ID, string text, and public record sentiment result, GUID-ID, string sentiment, double confidence, define our domain models using C#9's record type. Records are immutable reference types that are perfect for data transfer objects, DTOs, like these, ensuring that once a request or result is created, its content doesn't unexpectedly change, which is a good practice for message passing in distributed systems. Here, we introduce Inference Engine, which simulates the core AI workload. Notice that we're simulating a heavy computation at line 9. In a real-world scenario, this would be where an AI model, like a large language model or a computer vision model, is loaded and executed. Private static read-only random_RNG equals new, at line 12 is a thread-safe way to generate random numbers. Using a static instance of random is important to avoid issues with seeding multiple random instances too quickly, which can lead to them producing identical sequences of numbers, especially in a high concurrency environment. This inference engine will be instantiated within each AI agent, representing the actual brain of our AI service. The predict async method in our inference engine is where the simulated AI inference happens. Look at line 17, await task, delay, _RNG, next, 100, 500. This is a critical simulation of latency. Real AI inference, especially with large models or on GPUs, is not instantaneous. This task, delay mimics the processing time, which directly impacts the throughput of our AI agents and thus drives the need for scaling. The sentiment and confidence at lines 20 to 21 are simple placeholders. In a production system, these would be the actual outputs of an ONNX runtime, TensorFlow, PyTorch, or other ML framework inference. The use of async task is fundamental for non-blocking I/O and computation, allowing a single AI agent to handle multiple requests concurrently without blocking the thread pool, which is essential for high-performance cloud-native applications. Now we move to the AI agent class, which is a core component. This class represents a single instance of our AI service, much like a single Kubernetes pod. Notice the comment at line 28, represents a single pod running the AI workload. This is a direct analogy to how microservices are deployed. Each AI agent contains its own inference engine, line 31, simulating that each pod has its own copy of the AI model and inference logic. The channel is sentiment request _Q, line 32, is vital. It acts as an internal, in-memory queue for incoming requests, decoupling the request reception from the actual processing. This queue is a classic producer-consumer pattern implementation, enhancing resilience and throughput. _agent ID and _process count are internal metrics for monitoring and identification. In the constructor for AI agent, we initialize its unique _agent ID. More importantly, at lines 39 to 43, we create a bounded channel sentiment request. This is a critical design choice for cloud-native applications. A bounded channel has a fixed capacity, here, 10. This prevents an unbounded queue from consuming all available memory if the agent is overwhelmed with requests faster than it can process them. The full mode equals bounded channel full mode. Wait means that if the queue is full, any new try except request call will block until space becomes available. This backpressure mechanism is essential for stability, preventing cascading failures and ensuring that overloaded services don't crash but instead signal their inability to accept more work. This directly ties into resource management in containers, where memory limits are strict. These properties expose key operational metrics for our AI agent. Agent ID provides a unique identifier, crucial for logging and management in a distributed system. Queue depth, line 47, exposes the current number of requests waiting in the internal channel. This metric is extremely important for our horizontal pod autoscaler, HPA, simulation. It's a custom metric that the orchestrator will use to decide when to scale. Processed count, line 48, indicates how many requests this specific agent has successfully handled. In a real Kubernetes environment, these metrics would be exposed via Prometheus endpoints or similar monitoring agents, allowing the HPA controller to collect and act upon them. The start processing async method, line 53, simulates the actual work loop of our AI agent, akin to the main process running inside a Docker container. Notice the comment at line 51, simulates the Kubernetes container entry point. This method continuously reads from the internal queue using a wait for each, var request and _queue, reader.readAllAsync, cancellation token. This asynchronous loop efficiently processes requests as they arrive without blocking. Each request is passed to the _engine.predictAsync method for inference. Interlocked, increment, ref_process count, is used for thread-safe incrementing of the counter, ensuring accuracy even with multiple concurrent operations. The comment at line 58, in a real app, we would send result to an output sync, highlights that processed results would typically go to a database, message queue, or another service. The try except request method, line 61, is the external interface for pushing requests into an AI agent. It uses _queue, writer.tryWrite, request. This method is non-blocking and attempts to write a request to the channel. If the channel is full, due to the bounded channel options we set earlier, try_write will return false immediately, indicating that the agent cannot accept more requests at that moment. This is a crucial part of our backpressure mechanism. Instead of blocking the caller, it allows the orchestrator to quickly identify overloaded agents and route requests elsewhere or trigger scaling actions. This is a pattern for building resilient microservices. The stop async method, line 66, is designed for graceful shutdown. When an agent needs to be scaled down or restarted, we don't want to abruptly terminate ongoing processing. By calling _q, writer, complete, we signal to the channel that no more items will be written. The read all async loop in start processing async will continue to process any remaining items in the queue and then gracefully complete once the queue is empty. This ensures that all in-flight requests are handled before the agent fully shuts down, preventing data loss and improving the reliability of our distributed system. This is a common pattern for handling SIGTERM signals in containerized applications. Here we introduce the HPA Orchestrator, which is a simulation of Kubernetes Horizontal Pod Autoscaler, HPA, controller. This is where the magic of autoscaling happens. Private read-only concurrent dictionary string, AI agent _agents equals new, at line 73 is a thread-safe collection used to keep track of all active AI agent instances. Using concurrent dictionary is essential because multiple threads, e.g., the scaling loop and the request router, will be accessing and modifying this collection. _max agents and _target queue depth per agent are configuration parameters, mirroring HPA's max replicas and target average value for custom metrics. These parameters allow us to tune the scaling behavior, defining the upper limit of agents and the desired workload per agent. The HPA Orchestrator constructor initializes the scaling parameters, _max agents and _target queue depth per agent. These values directly influence how aggressively and how much our system will scale. For instance, a lower _target queue depth per agent means the HPA will be more sensitive to increased load and will scale out more quickly. Current agent count at line 83 provides an easy way to get the current number of active AI agent instances. The getTotalQueueDepth method, lines 85 to 88, simulates the Kubernetes metric server. It aggregates the queue depth from all currently running agents. This aggregated metric is the custom metric that our HPA logic will use to make scaling decisions, demonstrating how HPA can react to application-specific metrics beyond CPU or memory. This calculate desired replicas method, lines 91 to 108, is the heart of our HPA simulation. It implements the core scaling algorithm. At line 97, it calculates the total depth across all agents. Then, at lines 100 to 101, it applies the standard HPA formula for custom metrics, desired equals ceil, total queue depth / target depth per agent. This formula ensures that we aim for a number of agents that can collectively handle the current total queue depth while maintaining the _target queue depth per agent. Lines 104 to 106 clamp the desired replica count between a minimum, 1, ensuring at least one agent is always running, and a maximum, _max agents, just like Kubernetes HPA respects min replicas and max replicas. This logic directly translates to how Kubernetes would determine the number of pods needed for a deployment based on custom metrics. The managed scaling async method, lines 110 to 158, represents the continuous control loop of the HPA controller. It runs indefinitely, periodically checking metrics and adjusting the number of agents. Look at line 114, await task, delay, 2000, cancellation token. This simulates the HPA's sync period, which is how often Kubernetes re-evaluates scaling decisions, typically every 15 to 30 seconds, but we use 2 seconds for faster simulation. The cancellation token is crucial for gracefully shutting down this background task when the application itself terminates. This loop is the autonomous brain of our auto-scaling system, constantly striving to match the workload with the available processing capacity. Within the HPA control loop, after a delay, we calculate desired and current replica counts, lines 118 to 119. If desired the current, we enter the scale-out logic, lines 121 to 133. This means the current agents are overloaded, and more capacity is needed. We determine scale-out count and then loop to create new AI agent instances. At line 127, a new agent is instantiated with a unique ID. _agents.triad adds it to our active agents collection. Crucially, at line 130, _equals new agent.start processing async, cancellation token, starts the new agent's processing loop as a fire and forget background task. This mimics Kubernetes spinning up a new pod and starting its container, allowing it to immediately begin accepting requests. The console output at line 132 provides visibility into the scaling actions. If desired current, lines 135 to 157, it means we have more capacity than needed, and we can scale in. This is a more delicate operation. In Kubernetes, scaling in involves marking pods for termination, and the application typically receives a SIGTERM signal to perform a graceful shutdown. Our simulation handles this by first determining which agents to remove. At lines 142 to 146, we select agents with the shortest queues and fewest processed requests. This strategy aims to remove agents that are least busy, minimizing disruption. For each agent to be removed, we call removedAgent.stopAsync, line 152, which gracefully completes its internal queue before the agent is effectively decommissioned. This ensures no in-flight requests are lost, a critical aspect of reliable microservice operations. The route request method, lines 160 to 175, simulates a load balancer or an API gateway that distributes incoming requests to available AI agent instances. This is a crucial component in a distributed system, as it determines how effectively the workload is spread across your scaled-out services. Here, we implement a simple least connection or least queue depth strategy, lines 164 to 166. We find the target agent with the shortest internal queue. This is a common and effective load balancing technique for stateful services or services with varying processing times, as it ensures that new requests go to the agent most likely to process them quickly. If the chosen agent's queue is full, target agent.try-except-request, at line 170, a warning is logged, simulating how a load balancer might retry or return a 503 error, providing backpressure to the client. We've reached the program class, which serves as our simulation driver. The main method is the entry point. At line 186, we initialize our HPA orchestrator. Crucially, we configure max agents, 5 and target queue depth per agent, 3. These parameters are vital for observing the scaling behavior. Max agent sets the upper limit on how many AI pods can be active, mirroring a resource constraint in a real cluster. Target queue depth per agent dictates the desired average number of pending requests per agent. If this value is exceeded, the HPA will attempt to scale out. These settings allow us to control the cost and responsiveness of our simulated microservice. Here, using var CTS equals new cancellation token source, initializes a cancellation token source. This is a standard .NET pattern for managing the cancellation of asynchronous operations. It allows us to signal to our long-running tasks, like the HPA control loop and the monitor, that they should gracefully shut down when the simulation concludes. At line 192, var scaling task equals HPA.manage_scaling_async, CTS token, starts the HPA orchestrator scaling logic as a background task. The CTS token is passed to it, enabling proper cleanup later. This mimics a Kubernetes controller running continuously in the cluster, independently managing the deployment's replicas. This block simulates incoming traffic. var traffic generator equals task, run, async, equals, creates a background task that continuously generates sentiment request objects. The loop at lines 198 to 207 simulates a burst of 5 requests every second for 20 iterations, mimicking a sudden increase in user demand or a flash sale scenario. Each request is given a unique GUID and a descriptive text. HPA.routeRequest (REQ) is the critical line where each generated request is fed into our orchestrated system, which then decides which AI agent should handle it. This traffic pattern is designed to put pressure on the system and trigger the auto-scaling mechanism, allowing us to observe its effectiveness. The monitor task, lines 210 to 219, is another background task that provides visibility into our simulation. It periodically logs the current number of active agents and a placeholder for total processed requests. Await task, delay, 3000, CTS token, ensures that status updates are printed every 3 seconds, allowing us to observe the system's state changing over time. In a real-world scenario, this monitoring would be handled by tools like Prometheus and Grafana, collecting metrics from the HPA controller and individual pods. The comment at line 217, note, in a real app, we'd aggregate process count from agents, highlights that for a truly accurate total processed count, we would need a more sophisticated aggregation mechanism, perhaps by having agents report their counts to a central metric store. Finally, we await the traffic generator task, line 221, to ensure all simulated requests have been sent. After the traffic burst, await task, delay, 5000, provides a grace period, allowing the existing agents to process any remaining requests in their queues and for the HPA to potentially scale down. Then, CTS cancel, signals all cancelable tasks, HPA and monitor, to shut down gracefully. Await scaling task, waits for the HPA control loop to complete its graceful shutdown. This structured approach to starting and stopping tasks ensures that our simulation cleans up properly and demonstrates best practices for managing asynchronous operations and application lifecycle in .NET, especially in cloud environments where processes need to respond to termination signals. Thank you for your attention. This lesson is excerpted from Volume 7, Chapter 10 of the C# and AI Masterclass ebook series and from the volume Cloud Native AI and Microservices, Containerizing Agents and Scaling Inference. You can find all the details here, https://github.com/edgarmilvas/C# programming series. The ebook also includes diagrams, advanced examples, and 5 exercises with solutions for every chapter. There are 26 chapters. If printed, it would exceed 600 pages. Subscribe to the channel to watch more videos. I look forward to seeing you in the next lesson.